You may already know that when electricity passes through any material, like say this wire over here, then it starts producing heat. This is the same reason why your mobile phones tend to get hot when you play games on them. So on one hand, we could say this is a wastage of electricity, because some of the electrical energy is getting converted into unwanted heat. But on the other hand, this means we can now create heat from electricity. We don't have to depend on fire anymore. And so this is the principle behind your iron boxes today, or maybe electric toasters, or even light bulbs. The light that we get is because of the heat that is generated due to electricity. And of course, an extreme example would be when lightning strikes a tree, the heat produced is so much that it catches fire. So, whether it's for good or bad or worse, in this video we will see why does electric current, which is just a flow of electrons, produce heat. And we'll also learn how to calculate the amount of heat generated due to the electricity. Alright, so let's first begin with the name of this phenomenon. This is simply called the heating effect of electricity. But it's also often famously called Joule heating. And that's because it's this guy, James Joule, who was the first person to study the relationship between electricity and heat in detail. And if you're wondering, then yes, the SI unit of energy, Joule, is named after the same person. But let's come back to our question. What causes Joule heating in all these cases? Well, the main reason for this is collision between electrons and atoms. So let's look at that in a little bit more detail. So to understand where this heat comes from, let's zoom into this wire, and let's say we zoom in all the way to the atomic level so that we can see the individual atoms that make up the wire. Now when we have an electric current, basically there are electrons flowing through this material. Now here's the important thing. These electrons don't flow in straight lines. Instead, whenever they encounter an atom in their path, they bounce off of these atoms. So these electrons are continuously colliding and bouncing off of different atoms as they move forward. And during the collision, these electrons transfer some of their energy to the atoms. Think about it. It's like a very small stone coming and hitting a big stone. It transfers some energy to that big stone, isn't it? Similarly, the electron transfers some energy to the atoms, and as a result, the atoms start shaking. They start jiggling. And now you can imagine what would happen if we had lots and lots of electrons, going and colliding with these atoms. These atoms start jiggling a lot. And whenever the atoms of any material start jiggling, that's when the material heats up. So basically, whenever we have an electric current, whenever we have electrons flowing through any material, because of the collision between the electrons and the atoms, the electrons transfer some of their energy to the atoms, making those atoms jiggle, and as a result, the material gets heated up. Okay, now that we have some idea behind how Joule heating works, let's go ahead and see if we can figure out a connection between the amount of heat generated and electricity. And for that, let's get rid of this picture and consider a filament of light bulb. Let's say that the current through the light bulb is I, and let's assume that the potential difference across the filament is V. Now to calculate the amount of heat generated, all we need to do is use energy conservation. You see, we know that it's the electrical energy that's being converted into heat. So for example, if we find out that 100 joules of electric energy is being lost every second, then it means 100 joules of heat is being produced every second. So you see, all we need to do is calculate how much electrical energy is lost over here every second, and then we are done. And we've already seen in a previous video how to do that. We've seen that the amount of electrical energy that is lost or gained per second, which we often call electric power, turns out to be just the product of voltage and current. And if you're interested in knowing where this comes from, then we have discussed this in great detail in a previous video. So it will be a great idea to go back and watch that video for this. But anyways, this number tells us how much electrical energy is being lost every second. And since it's being converted to heat, it also means this tells us how much heat is being generated over here per second. So this number, so let's write that down. This number, okay, this represents heat produced per second. So in 1 second, this is the amount of heat generated. In 10 seconds, well, the heat generated will be 10 times this number. And so, in general, we can now write the amount of heat generated will be this number, the amount of heat generated per second, times T. And there we have it. It's not a new formula because we already knew how to calculate electric power lost or gained. So this formula tells us that if we have more current, then we have more heat generated. And that kind of makes sense. If we have more current, then there'll be more electrons passing per second. And as a result, we will have more collisions happening per second. And so we'll have more heat generated per second. The formula also says more voltage means more heat. Why is that? Well, remember, voltage is potential difference, which is an indicator of how much potential energy these charges have, these electrons have. And so more voltage means they have more energy. And I'm pretty sure you agree, if something were to come and hit these atoms with more energy, the atoms would vibrate more rigorously, more violently. And as a result, we would expect more heat to be generated. When lightning strikes a tree, the voltage and current are both super high. And as a result, the heat generated is incredibly high, enough to burn that tree. Alright, what if we don't know the voltage and the current, but maybe we know the voltage and the resistance, or maybe the current and the resistance? Can we still calculate the amount of heat generated? The answer is yes, because we know what's the connection between voltage, current, and resistance. Ohm's law. It tells us that voltage is current times the resistance. And so what we can do is, in this formula, substitute for V as IR, and then we'll get IR times I, and so that will give us I squared R times T. So this is another formula in terms of current and resistance. And similarly over here we can substitute for I as V over R. In that case what we would get is V over R, so V squared over R, times T. And this is a formula that tells us how much heat is generated in terms of voltage and resistance. And these are not three different formulae. These are all identical formulae. They all come from the same one. So don't think about them as three different ones. Basically, this is our formula, and we just substitute Ohm's law and we get the other two. So that's pretty much it. But before we conclude, I just want to talk about a couple of technical details. One is, whenever we have heat generated due to electricity, we often term it as power dissipated. So if you're ever asked to calculate the power dissipated, we basically have to calculate how much heat is generated per second. And the second thing is, when Joule was doing the experiment to figure out the relation between electricity and heat,